Alright, so now we're going to do an analysis of singly linked lists. And the analysis will hold true for a doubly linked list as well. We'll just go over that again for a doubly linked list once we get into the tail. But I want to just emphasize why this is a thing we like to build, okay? The first thing we need to do is we'll take care of the easy one. What is the runtime of this? Well, we're returning of size. Well, we're returning a variable, so that takes no time at all. Constant time, it's just returning a variable, same as an array list, right? What about the get node? We're getting a node at index, at this given index. Okay, so how do we do that? Well, this is the key to understanding the vast big differences between our runtimes. So to get a node, we have to start. Sorry, to get a node at a specific index, we have to start at this at the head of the list, and then we have to follow the .nexts manually. So we have to manually go through and basically do this assignment statement until we get to the appropriate index. So sometimes I'm going to want to get this note something at the very beginning. Sometimes I want to get something at the very end. But on average, it's going to be somewhere in the middle of n items. So on average, I'm going to traverse n over 2 items, which means that anything that uses get node will be O of n time, right? Anything that calls this is calling an O of n method because it needs to, unlike an array list, which I can instantly teleport to an index and just grab it, I have to manually walk to that index starting from the head, right? Even if I have a tail, I'd still have and calculate is it closer to the head or to the tail, I'd still have to walk backwards, right? It would still be a linear relationship. I'd still have to manually walk through it. I can't magically teleport to any node except for the head. So that informs a lot of our of how these will work, right? So the add method has 3 scenarios. Well, this scenario is constant time, just checking to see if the index is out of bounds. Okay? If we're adding a new head to the list, if we're adding on to the very beginning of the list, okay, then what happens? Well, I just basically change around one memory location and I change around another memory location. I'm doing 2 assignment statements. Doesn't matter how big the list is, we always run these 2 commands if I'm adding a new head to list. So adding a new head, adding something beginning to the linked list, takes constant time, and that makes sense. That makes a whole lot of sense, because if I'm adding something to a linked list, ignore the other stuff that I've already drawn, all I'm doing is creating a new node, bam, and then basically attaching it like that. It doesn't matter how many items there are in the list so far. There could be 10 items, there could be 1 item, there could be a million items. It's just basically create a new square, draw an arrow. Doesn't matter how big the list is, that's going to take constant time. Okay? Everything else, well, we have to walk to the node before the node we want to insert. So this takes O of n time, because we have to go to the guy before the one we want to remove. And then we swap around 2 memory locations. Okay, this takes a constant amount of time, this takes a constant amount of time. So this third clause, adding anywhere else besides the head, takes O of n time. So linked lists are great at adding to the head. And if you have a tail variable, we'll see that basically having a tail, it's the same thing where you just manipulate a couple memory locations and you're done, right? It takes constant time to add to the end if you're keeping track of the tail. But if you're not keeping track of the tail like we're doing in here, adding to the head's constant time, but adding anywhere else, it's as horrible as having an array list, which is that I have to shift stuff over for the array list, and here I have to iterate to the location and swap memory locations. But this is very good for if you're consistently adding something to the beginning of the linked list, or if we're keeping track of the tail, as we'll do in the next example. We'll keep track of if we keep track of the tail, then it's going to be constant time for adding to the end. And you can see that it's basically very obviously the same for the remove method, right? this takes constant time. We're swapping around memory locations here, constant time. We have a get node operation over here, so it takes O of n time, right? We have to get the node before we remove. So it just depends on what you're removing for linked lists. What about the get and set methods? Well, those take O of n time because they will, as you're about to see, they rely on the get node method as well. So public e get int index, right? First thing I have to do is I'm just going to copy this over here, and I need to be able to get a valid index. So the valid indices are not, it's an invalid indice if it's less than 0 or greater than or equal to size for get, because we're getting a valid index. You can always add on to the thing behind the last index, but not for get method. Okay. Otherwise, what we'll do is that we return get node, the index, item, like that. And that's all we need. Similarly, for the set method, e set index, set a specific index to e item. What we do here is that we instead, I'll need this a bit more. So e to return is equal to, we'll just leave that there for right now. E node, so, and then node e node. And because we're not doing any manipulation, I can just simply go directly to the node at the index, right? We only have to go before because we're manipulating in the add method or the remove method because we're manipulating the pointers around. So we go to the index at that location, and we are going to get the node, and then we are going to, let's see, sorry about that. So we get the node at the location, we get the item there, we then change out the item there, node.item is equal to the item that's been submitted, and then we return to return. And again, these take O of n time because they have this get node in there, which as we saw takes O of n time.